Hello, in this segment we're going to learn about revolving functions around an axis to form a solid figure and thus calculating the volume of that figure. We'll start out with this example. I want to take this function right here that is above the x-axis and I want to revolve around the x-axis. That means that this figure is going to swirl around like this, and it's going to carve out a kind of round ball-ish shape. It's going to be solid because the area that we're dealing with is touching the axis of rotation. You don't need to really think about that, but just to kind of throw that out there, that's a something to watch for. If this was not touching the axis of rotation, if we're rotating around the line, maybe y equals -2 or something, we would have a hollow portion in our ball. But anyway, I really encourage you, don't think about that yet. So what we're doing is we're going to have a bunch of discs basically created. Like this disc, this disc, this disc, smaller one, and we're going to take all these discs and they're all going to have a thickness of dx, a uniform thickness. There's an infinite number of them. And the volume of a disc is pi r squared h. So the h is going to be dx. The radius is going to be different for every single one. It's going to be, here's the radius there, there's my radius there, there's the radius there. And so the radius is basically the distance from the center. This is the center, the axis of rotation, to the outside curve. I'm going to call that the outside radius, RO. So this curve represents the outside edge of the figure. And so this function is going to be this function minus that axis of rotation, which is sine cosine minus 0. That is going to be my radius. So my volume of one disk is going to be pi r squared h, where r is sine cosine. And then the total volume will be the integral of that. And it's going to happen from starting at 0 and ending wherever this crosses the x-axis, which is not really given. So we're going to have to figure that out real quickly by typing in, clear all this out, sine times cosine. I'm just going to do a zoom standard. You can see my picture is really not very a good graph. It's not very zoomed in. Maybe I'll do zoom trig. A little bit better there, but still not, it's good enough. I want to know where that little first segment is. That's what I'm looking at. So I'm going to do, and I might actually just zoom this in a little bit more just for laughs. Maybe we'll do 2 and 2. And so you can see this one more time. And I'm going to go to second calc, find the 0 of this function. We'll say a left bound is this, right bound is this. I guess can be right there. It's at 1.57, that's half pi. So this is going to be half pi right here. So we're going to integrate from 0 to pi over 2. That is an integral that expresses that total volume of the figure. Don't spend a lot of time worrying about what the figure looks like. Here it's pretty easy to tell it's a ball, but in general, I'm more interested in the conceptual nature of this rather than the, finding the volume rather than the art. If we did this again with the same function but rotated it around a different axis, we'll see kind of how that would compare. So we've got that again. We know that's half a pi now. We know this is y equals sine cosine. I'm going to rotate around y equals -2, as I kind of mentioned in the last bit. Right now, this is my axis of rotation, right there. So now, this is still the outside surface, and that radius, I'm going to call the outside radius. But instead of this being a solid ball, this time we're going to have an inside radius that kind of carves off an inside part. We'll have kind of a ball with a hole going through it, a disc with a hole in the middle of it. So the distance between, this defines the inside surface, y equals 0. The difference between there and the axis of rotation, I'm going to call the inside radius. And my logic is for a certain disk, it's going to be pi r outer squared times h minus pi inner squared times h. The h is still dx. The thickness of all those disks is still dx. And so all you need to do is kind of fill in the blanks. The total volume here is going to be 0 to pi over 2 again, pi times outer radius squared minus the inner radius squared, all times dx. The outer radius is sine times cosine minus a -2. That. And then the inner radius is 0 minus a -2, so this would just be, write that again a little bit better. Sine cosine plus 2 squared minus 2 squared dx. This is the solid portion minus the carved out, in this case just a tube going through that ball portion. Let's look at this example. Here we've got a region, let's call this the region here. It's between the curve y equals 4 minus x and then y equals 1/4 plus sine of pi x. And I'm going to just start this, revolve this around the line y equals -1. Right there. So even though this is something that I probably don't want to try and imagine what the shape would look like as this goes around and around and around and around. Obviously, it's going to have a big hollow portion in the middle. Maybe it's going to look kind of like a big tulip opening somehow. Not really sure. But I do know that the outside radius, this defines the outside surface. The outside radius is this. That's the outside radius. And then this line, the 4 to the minus x, defines the inside radius. And do r sub I. And so let's just write those down. I didn't before, but the outside radius is going to be this curve, which is 1/4 plus sine of pi x minus a -1. The inside radius is going to be 4 to the -x minus a -1 here to here, top minus bottom. And so now if I write the total volume, we're going to integrate from here to here. Uh-oh, I don't know what those are. I have to figure that out. It's going to be the pi times the outer radius squared. So it's going to be 1/4 plus sine pi x plus 1 squared, and then minus this, 4 to the -x plus 1 squared dx. So I need my limits of integration. That's my last piece to the puzzle here. And I'm just going to have to find that on the calculator because I sure don't know what they are. Uh, 4 to the -x, and then sine x plus cosine x. Oh, no. How about 1/4 plus sine of pi x. Keep in mind you need to make sure you're in radians when you do this. You can see I'm in radians. All these problems should be in radians. So let's just graph this, see what we're looking at. So I'm looking at this little region right there. I'm going to zoom way in on it so I can not be distracted by all the other things around. We'll do x's 0 to 1 maybe, and y can just go down to like -1. There's my 4 to the negative x. Cool, that's just about right. I want this region right here. I might actually just go out a little bit farther, 1.5, just so you can see it really well. Okay, so I want to find that intersection, and that will define my region. I'm going to go to Calc, find intersect. First curve is that one, second curve is that one. It says guess. So I'm going to go over and say I want to guess this first point. It's thinking about it. 0.1782. And then the second point, second calc. That curve, and then the second curve, that one, and then it says guess. Calculator's kind of slow. One. Okay, that's why I had to stretch it out a little bit. So this integral will give you that volume. I'm not evaluating these integrals on camera. It's really just kind of a calculator integral, I would say. I'm not going to try and do this by hand. I certainly wouldn't try. But anyway, that's the logic between it. Pi r squared h for the big one, pi r squared h for the little piece that's taken out, subtract them. And you know, if you could call this v sub I if you didn't have the integral, indicating one of the infinite number of disks, and then integrating allows you to kind of add them all together. Let's do one with respect to the y-axis. Okay. I'll just start with kind of a relatively simple one, or just a linear. This is going to be the line x plus 2y equals 2. And, oh, hang on, it is not that line. Let me draw that again. X plus 2y equals 2. One more time. We've got 2 and 1, and this line's going to kind of look like that. That's my region. This time I'm going to go revolve about the y-axis. That means that my outer surface is, and this is going to be kind of a, not that I've told you not to kind of think about it, but it's going to be kind of a cone shape like that. So this time the outer radius is right here. The outer surface defined right there is this part of the line. So I'm going to say that's outer radius. And notice it does not have an inner radius. The inner radius is 0 because it's solid. Because the region touches the graph itself, that tells me that it does not have an inner radius, or I would say the inner radius is 0. So to start kind of identifying outer radius and inner radius algebraically, keep in mind that your disks this time are going to stack like that. There's a disk. There's another disk. And so the thickness is dy this time. And so this needs to be solved x in terms of y. So that's your equation this time. And the outer radius is going to be the right minus the left, which is 2 minus 2y, and then effectively minus 0 for the if you did right minus left. This is the line x equals 0. For the inner radius, it's 0, so I don't really need to write that down, but for consistency, I will. So my volume of a single disk, VI, is pi 2 minus 2y squared dy. And my volume total is going to be pi 2 minus 2y squared dy. And on the y-axis, we do this from 0 to 1. So that would be my final volume for that figure, this kind of cone-type shape. And while we're here, let's just do this again, revolving it around a non-y-axis, maybe x equals -3. And just try this same problem again. Two minus 2y. We've got this figure. What did I say? We said minus 3. So this is my axis of rotation now. And so this figure right here is going to whirl around. Suddenly it's not going to be a cone. It's going to be like a volcano. It's going to be like this, with the kind of open part in the middle. Again, it doesn't matter if you can think of that or draw it, but I don't know, you might like to know. It kind of looks like a volcano. It's going to have a big open bit in the middle. So anyway, this is whirling around now like this. And the outer surface is defined by that line. The inner surface is defined by this y-axis. So I've got my outer radius here. And I've got my inner radius right here. Right down the outer radius is going to be 2 minus 2y minus -3. That's right minus left. And the inner radius is 0 minus -3. Again, right minus left. And so my total volume will just kind of jump to that. It's going to still be happening from 0 to 1 on the y-axis. It's going to be pi times the outer radius squared, 2 minus 2y plus 3 squared, and then minus the inner radius squared, which is 3 squared, and then dy. And you can evaluate that integral yourself. But anyway, that is just kind of in a nutshell how you do problems both that have a open area inside, a hollow area, and then ones that are solid. Now, in any textbook, this is the washer method, and then the former is the disk method. And in my opinion, I don't like those methods. They make the problems seem like they're different types of problems, and they're really the same type of problem. If you have an open spot, the inner radius is, in this case, 3. It's something. If you have a disk style problem, as they call it, the inner radius is just 0. But I really, really encourage you to think about these problems as the same thing. You know, when you see washer and disk, you know, they're the same kind of problem. The disk problems that don't have a hole in it simply have an inner radius that's 0. So I hope that helps out. This is like I said, an introduction to solids rotation.